There we go. Yeah. Now we're rolling. Here we go, folks. Logistic growth. Now, let me tell you why we have these different growth formulas. Exponential growth, or decay, exponential, is awesome in controlled environments or with radioactive decay. All right? You get this nice pattern, it decays, it decays, it decays. Or, as long as there's enough food, enough water, enough space, if you're growing cells in your lab, okay, you got your little petri dish and you're growing cells, you may not know it, but they actually grow human cells in labs, right? Y'all know that, right? One of the groups of cells that they grow are called HeLa cells. And does anyone know anything about HeLa cells? If you go over to med school and you're walking around in the labs, you're going to find cell test tubes that are marked HeLa cells. Okay, it's all right if you don't know. Giving you a chance. Okay, HeLa cells are named after Henrietta, and I may have spelled that wrong. Henrietta. Oh gosh, look. Henrietta Henrietta. All right. Catch is, yeah, and I'm sad I can't think of her name right off. Henrietta Lacks. Lacks, I think. I'm on. Put a question mark there, and I may have spelled Henrietta wrong. But here's the deal. Henrietta Lacks is the first human that they were able to grow her cells outside of her body. Okay? They'd been trying to grow human cells outside the human body for scientific use. Think about it. You've got all these human cells that you could test with. Fair enough? Is that all right? And at Johns Hopkins, she was a cancer patient at Johns Hopkins. And they took out her cancer growth, which was a very fast-growing tumor, and they sliced it up and they began to grow it in the little petri dishes. And it is her cells are the first human cells that were grown and able to continue to grow outside the human body. Okay? Now, when they were naming cells early on, they just named them after the first two letters of your first name, first two letters of your last name if they were using your cells. The fellow that did it originally didn't make money off her cells. But another fellow that was not as honest and was willing to rip people off began to sell her cells to other hospitals and to researchers and all that. The original couple, which was a scientific couple, a husband and wife, that learned how to grow cells and grew her cells, they did it and gave them away for people to use to learn how to treat cancer and all that. Her cells have been to the moon. Her cells have been were used for most of the vaccines that we have now. Her cells were used for, okay? Because we have a very good genetic history of her cells. We know what the DNA looks like and all of that. I shouldn't say we, but the science people do. If you're in the lab and you're handling cells, and they're human cells, remember they came from someone, and in her case she died of the cancer. She died soon after they started treatment because her cancer was such a fast-growing cancer. Her cells are still growing, still reproducing, and that's 60 years later, 50 years later, and her cells are still out there multiplying and multiplying. Her cells grow so well that if you have her cells in a lab and you're using her cells over on that side of the lab, and you got the hood that sucks everything up so that it doesn't get out in the room, If her cells get out in the room and they land on a petri dish over there, they just start growing. Okay? I mean, one of the problems with the HeLa cells is they will take over your lab and start growing on all your other stuff. That's how easy, if they get in the air or whatever, that's how easy they grow. The couple that started it, I always like to mention that they didn't make money off of it, but another guy made millions and millions of dollars off of it. Her family never knew until maybe 20 years ago that this man was making tons and tons of money off of her cells, and the family was living very, very poor and barely scraping by. Okay? And the fellow that, but the original pair didn't do that. It was another guy at the hospital. But Henrietta Lacks. Learn about her, know about her. She lived in Virginia, and she worked on a tobacco farm. All right? And that may have been the reason she got the real bad cancer. I don't know. I'm not a medical person, so I really don't know. But HeLa cells. But what happens with these cells, or with a lot of things in a controlled environment, is if you just let them keep growing and keep growing, they can grow for, you know, as long as you get more food, more space, they just keep growing. Fair enough? This is not a very good model if you're talking about out in nature. Because is there really always enough food or enough space? No. If you're talking about the spread of a disease, this is not a very good model either, because there's a maximum number of people out there that can get the disease, right? Okay. That's what logistic growth deals with. Logistic growth deals with the idea that you can get this increase that's really steep and fast, but like the spread of a disease, you can get this increase that's really fast, but eventually it will taper off. And it will taper off close to some maximum population. This fits what happens when you introduce wolves into Yellowstone. They know that there's only, the environment in Yellowstone can only support a maximum number of wolves. When you first release the wolves into Yellowstone, the population increases very fast. Then it reaches a point, key point right here, where it's still increasing, but it's increasing at a slower rate. And then the wolves get up to about the maximum population that can be sustained. And here's what's scary. When you're close to that maximum population and a disease breaks out, it spreads very, very fast. You get the same thing going down. Okay? The population of the wolves is going to drop off real sharp if a disease breaks out. The elk that live in not Yellowstone, Grand Tetons. The elk that live in the Grand Tetons area, they have this problem because their population goes up really fast and it tapers off, but in the winter the elk come out of the mountains and they get real close together. Disease breaks out in the herd and it spreads very, very fast because they're up in this part. Okay? Then they'll get a drop and then they'll do this again. Okay? But this is called logistic growth because it takes into account that there's a maximum population that can either live in that area, or with the spread of coronavirus, we run into there's a maximum number of people in America. Right? Now, if you take that, I'm going to try to explain to you what is happening with the coronavirus. And here's the deal. Okay, time is this way. Okay? Maximum population is this way. Maximum number of people that can get it. So what happens is the disease starts off and it goes up with this real fast spread. Folks, we're still down here. In the United States, we're still here. Okay? Now, what's going to happen though, here's what we would like to have happen. We would like to stretch the curve out. And instead of this happening in 1 year, which it's going to take more than 1 year, but instead of happening in 2 years, 10 years, 3, 4 years, we would like to stretch the curve out like the blue. Why would we not want it to spread this fast, even though it's going to go up to the same maximum? Why would we want to stretch it out like this in its spread?
The strain on our healthcare system.
Sir?
The strain on our healthcare system.
Yeah. Hey, folks, you were going to keep the numbers in the healthcare system smaller at any given point as it increases. Fair enough? Here, you got way too many people that have it. Ask El Paso right now. Okay, El Paso in their own city is doing this. They're like, El Paso's up here in their own city, but nationwide. Plus, what happens if you can stretch it out like this? Before it reaches, and these people get it, we may have a vaccine or a cure, yeah. In other words, if it spreads and it goes up this fast, before it gets to that maximum, and it happens real fast, you don't have time to react, you don't have time to improve the health system, you don't have time to find what you need. So the idea of wearing this mask, and you wearing your mask, is to slow this spread down and stretch the curve out. Now, if we stretch the curve out enough, we may not even have to deal with this part. The rate we're going now, but this is the curve that we want to avoid, where it's going up just real fast. Notice, they're both logistic growth curves. It's just what? We're stretching that one out. Fair enough? All right, well, let's talk about logistic growth. Now that you see that there is a reason for this one, because it deals with that maximum population. Biologists use this with, putting fish in a lake. They use it with the wolves at Yellowstone and all that. The change in the amount present with respect to time. That sounds familiar, doesn't it? Is jointly proportional to the amount present and the difference between maximum population and current amount. Okay. Amount present, current amount. All right. That's the words for logistic growth. And here's the catch about it. The other one only, the exponential growth only cared about the amount what? Present. This one also cares about the difference between the maximum and the amount what? Present. I don't like current amount. I'll put amount present. I think that looks better. Amount present. All right. So it's taking into consideration the fact that it just can't go up forever and ever and ever and ever. All right? Now, here is the differential equation for that. Jointly, there's the amount, and then the difference between the maximum and the amount. And with jointly, you multiply them. Jointly, if you learned when you were doing proportions, and y'all had jointly proportional, that's when you multiply the two parts together. If you had inversely proportional, you divided the two parts. I know some of y'all have long since forgot that from the 7th and 8th grade. I gave my speech yesterday about long-term learning. Of course, I can't remember how to spell Henrietta Lack's name, so maybe I did some long-term learning. This is the differential equation that those words mean. Change in amount present with respect to time is, there's your constant proportionality, amount, and then whatever the maximum amount is minus the what? Amount. Now, the good news is, yes sir, yes sir. The good news is, we don't have to know that formula at y'all's level, but when you get to college, they're going to show you how to turn that formula into the formula that you have to know. And here it is. The amount at time t is equal to the maximum amount over 1 minus some b value e to the kt. And that is the formula for logistic growth. And Mr. Evans is going to have to tell you there's a plus sign. Now, I'm looking over here. I got my notes on that formula. I hate to admit it, but I actually am using a little note. I always try not to have to use notes when I teach something, but I actually have the notes here. B to the EKT. Now, this formula, notice, does not have A sub 0 in it. It doesn't have the original amount in it anywhere, it doesn't. But it's got this weird B in here. All right? Well, let me help you out with that. If T is 0, then you have this huge amount over here. All right? You have whatever the amount is. Mr. Evans, just write the formula, and then they'll feel better. A sub 0. Well, I didn't know I was going to teach it this way. I thought I had the other formula written down, but I don't. A sub 0 is going to equal to the maximum amount over, and if you put a 0 here, e to the 0 equals how much? What does e to the 0 equal? 1. So you just get b. 1 plus b. So if you want to know how to find b, here's the formula. You put whatever the original amount is here, whatever the maximum amount is here, and you can solve for what? B. Somebody said, Mr. Evans, there's another way to do it. Absolutely right. Someone says B always equals the maximum amount divided by the original amount minus 1. Okay? Maximum amount divided by the original amount minus 1. That's what the B value always is. Either one of these formulas will find B. Notice, last time you learned about this, what was the first thing you found? A sub 0. Now you need B. Then, guess what? You can find K. And K is going to be done just like the other one. You're going to use some information to find K. Now, there's some other little bits in here that I want to talk to you about. Okay, these are going to have this general shape. They're going to go up real fast, and they're going to taper off at the maximum. See this point right here? That's where the tapering off begins. Here it's going up as fast as it can, and then it begins to do what? Taper off and go up slower. Is that okay? That point is crucial. That point is called an inflection point. This point, that's called an inflection point. And the value for that inflection point is always the negative natural log of the B value over the K value. And it's always the maximum divided by 2. Which I didn't believe it was always the maximum divided by 2, but it is. See, I got my little cheat sheet there. Now, how many of you have done pH in chemistry? This is pH. This is what pH does. It goes up really fast and then it begins to taper off. pH cannot go up forever and ever. All right? This is the formula for pH. When you do pH in chemistry, everybody hear that? This is the formula for what? pH in chemistry. All right, now it's like the students are going, Mr. Evans, just work the problem. Just show us how the problem works. Okay, we'll do that. Here's an example how it works. There's where it all comes from. There's the word, there's the real definition. Learn it, learn what the words mean. There's the differential equation. It will help you remember the definition. I actually remember the differential equation better than I remember the definition. And then, of course, I had to look that up and remember that was a plus sign. Oh, and to get from here to here when you get to college, or if you take my class next year, you take the engineering STEM class next year, I'll show you how to get from here to here. It takes a page or two. All right, it's a serious one. It's not an easy one. Here we go. So, we got a logistic growth situation. And we want to come up with the formula. And we want to see what's happening. And we know that the maximum number of Slimers is 500. Maximum number of Slimers is 500. Maximum number of Slimers is 500. And we know that because Captain Shreve cannot behave, that Captain Shreve let loose 5 Slimers. A sub 0 is equal to 5. After 7 days, they had 12 Slimers. We would like to know how many Slimers they will have in 31 days, or 30 days, let's do 30. And how long will it take for them to have 450 Slimers? That way we're doing everything possible. Okay? How many Slimers do they have after 30 days? How long to have 450 Slimers? Now, it took them a week just to spread from 5 to 12, right? But remember, the next week they're not just going to go up by 7. They're going to go up by more than 7, right? Because it's going to start off, if you'll notice, it starts off acting like an exponential curve until it gets to that inflection point. Until it gets to that inflection point, it's acting like that. Now, so here we go. We do A of t equals the maximum 500 over 1 plus b e k t. Now, ladies and gentlemen, please do not do everything at one time. You just put the maximum in there. Then, after you put the maximum in there, we will find the b value. And it turns out that Mr. Evans is probably about to be really irritated because he used 12 there, and that doesn't divide into 500 real easy. Because if I want to find the b value, I know that a sub 0, 5. A sub 0, 5 equals 500 over 1 plus b. Notice I'm having to do it the long way. I gave y'all 2 formulas, but I have to use this formula. Because when t is 0, that equals 1, and then I get that formula. So somebody tell me what b equals. B equals 99. B equals 99. Everybody okay that b equals 99? Now check it out. 99 plus 100. 500 divided by 100 is what? 5. Or multiply by the common denominator. Right? Y'all know how to solve that, right? Okay, yeah. I see somebody shaking his head up, down. I'm going to keep teaching. So, a sub t now equals 500 over 1 plus 99e to the kt. Yes, sir?
Can you do it the other way? So b equals max over original minus 1.
Yeah, b would equal 500 over 5 minus 1. Yeah. B would equal 500 over 5 minus 1. And guess what? You still get how much? 99. You can use either formula and you'll get B. I bet y'all like that formula a lot better, don't you? Yeah. All right. See, Mr. Evans should have thought about how he's going to teach this instead of just walking here in this morning and thinking, I better teach that. I had to look up and find my sheet. Okay, what do you think you have to solve for next? K. All right, let's find K. To find K, I need to use the 12 and the 7. Okay, I use this to find B. I use this to find what? K. Now, so 12 equals 500 over 1 plus 99, 7K. I'm going to work this one out step by step. I'm not going to try to do anything too fast. I'm going to multiply both sides by that. 1 plus 90, here's the e to the 7K. Can't believe I'm recording a lecture that I make that many mistakes on. They can tell, whoever's watching this, that Mr. Evans hasn't taught this in a while. I get 12, parentheses, 1 plus 99, e to the 7K equals 500. 1 plus 99, e to the 5K equals 500 divided by what? 12. I sure wish that would have divided into there perfect, but it doesn't. So far, so good? Just checking to see if you're awake. All right, now everybody agrees I'm going to do what? Subtract a 1. Agree? Yeah. Subtract a 1. So I'm going to get 99 e to the 7K equals 500 over 12 minus 1. And then after I do that, is everybody okay? Then we'll divide by 99. And you probably, at this point, have pulled out your calculator and started turning all this into decimals, which is okay with me. Just write out a bunch of places. Yes, sir?
What's below the 500 on that side?
500?
Below that.
12.
Okay.
Same, I'm not going to, I was about to say something mean. E to 7K equals 500 over 12 minus 1 divided by 99. And then what are you about to do to that? You're about to take what of both sides? Natural log. I strongly suggest at this point that you have turned it into a decimal. I'm going to. I'm going to pull out my trusty calculator to do that. I found out yesterday some of y'all are trying to do too many steps at one time. It's okay. I like it. Y'all are trying to learn. That's what matters. Y'all are learning. Okay. I'm going to take the natural log of that. And then I'm going to go ahead, and does everybody agree after I take the natural log, I'm going to have to divide by 7? Is that okay? Yeah, so I'm going to go ahead and divide by 7. Do it all in one step. And I get K equals, and your K should be a negative number. Somebody says, somebody wrote the formula different. Yeah. I get K equals negative 0.1271. I'll go ahead and write them all out. 0, 1, 5, 8, 4, 9. Now, if I was really writing this out, I'd only write out 4 of them on my paper, but just to show you that's what you get. Once you do that, you have the specific equation. Ladies and gentlemen, you must have the specific equation before you try to work any of the other parts of this problem. Okay? Find the specific equation. Now, I'm going to write out. Before I write it out, I want to make sure everybody's okay. Got the flow of solving for K. We'll write out the equation. Here we go. A of t